introductions. Hello everyone, welcome to a very special one-off public talk. It's very strange to see people here in the lights. We're normally sort of shivering under the foggy sky of these things. We have a very special visitor here with Professor Daniel Eisenstein, who's chair of the Department of Astronomy at Cambridge University. He's visiting us for a week, and he very kindly offered to give a public talk to accompany his academic lecture that he's treating us all with tomorrow. He's going to tell us all about something that astronomers have been very excited about over the last few months, all about exploring the early universe with JWST. So yeah, thank you, Dan.
Okay, thank you. But I'm not sure this is on yet. You're going to need to help me with the mic. It's not working yet.
It's hard to hear from down here. Most of the speakers point the other way.
Are people?
So I think that is apparently on.
Yeah, we're on. Okay. So it gets way further up. Okay. Can you hear me now better? Okay, great. All right. Well, it's really a pleasure to be here to share with you some of the work that we've been doing with the James Webb Space Telescope. And I'm sure that you've probably been following this in the news, and that's why you're here tonight. But it has been just a wonderful year with the first year of this telescope after so many years of planning. So my focus today is going to be on the study of galaxies in the early universe. So galaxies that are very, very far from us, very faint, very distant. There are lots of beautiful things about JWST, lots of very, very pretty pictures. We're going to be looking at the very, very, very small dots in some of these pictures. Okay, so let me start off with nearby galaxies. So of course, galaxies are really beautiful things. They're iconic. These are pictures from the Hubble Space Telescope. But galaxies are also really complicated. You're used to the sort of simple spirals, but then sometimes they come in mashed up pairs. Other times they have weird shapes. And we want to understand how these galaxies actually come to be. So before I can talk about galaxies, I need to say some words about stars, because I'm going to try to motivate why we had to build the James Webb Space Telescope in the way that we did to study these early galaxies. And so I need to tell you some of the backstory first. So let me just pass along some very brief ideas about stars. So of course our sun is a star, and stars form in a really wide range of masses, from something like 10% of the mass of the sun to 100 times the mass of the sun. And the mass of the star affects its properties a great deal. And in particular, massive stars, the most massive stars, have very high central pressures, very high densities, and this allows them to burn their fuel more rapidly, and so they are much more luminous. And they're also extremely hot, and so they dominate the light of galaxies in the ultraviolet. Whereas most stars are much lower mass, indeed lower mass than the sun, and they live for billions of years, sort of slowly cooking along, and produce light that is at a much lower temperature. So as I said, the hotter objects burn brightly, but also because they're hotter, the emission peaks further at higher frequencies or smaller wavelengths, further towards the ultraviolet. And in contrast, the cooler stars peak more at longer wavelengths in the near infrared. Our sun is kind of in the middle, peaking in the yellow and in the optical. So the reason I need to introduce those ideas is that, of course, galaxies are made of a wide range of stars. And when a bunch of stars form together, you form a few of the really high mass ones and a lot of the very low mass ones. And initially, of course, you're seeing mostly the really massive stars, because they're so much more luminous than everything else. But as time goes on, they die out, because the most massive stars only live for a few million years. And so as time goes on, 10 million years, 100 million years, a billion years, you are progressively, the higher mass stars are progressively dying out, and the death line moves to lower and lower mass, and hence the system appears colder and colder, redder and redder. So as a really important or beautiful example of this, the spiral arms that we're so familiar with in spiral galaxies are not due primarily to the fact that there's a lot of stars in the arms and few stars in between the arms. It's actually due to the fact that all of the young stars live in the arms, and those young stars are outshining all the rest of the stuff. So when we look at the spiral arms, we're primarily seeing the recent star formation, not large variations in how many stars there are from one place to another. So because of these variations, this is an example of why astronomers make such an emphasis on studying objects and galaxies in particular here across a really wide range of wavelengths, because every different wavelength of light across the electromagnetic spectrum is telling you something different about the properties of galaxies. So I've introduced the idea that ultraviolet and optical is telling you about hotter stars, and near-infrared is talking about colder stars. But we also study things in the mid and far infrared, where you're really studying the dust and molecules in the interstellar medium. We study things in the X-rays and gamma rays, trying to measure a very hot gas, such as around black holes. We study things in the millimeter and radio, often to study the relativistic electrons that are gyrating around in magnetic fields. So we're really trying to study things across a wide range of wavelength. This drives a really wide range of telescopes, wide range of instrumentation, but it's all because we're trying to study these objects from a lot of different perspectives and seeing the different components as we go. So as an example of this, on the left is a picture from the Hubble Space Telescope taken in optical light, like your eyes. And you can see that the big spiral galaxy at the bottom is kind of bluer and brighter, and the elliptical galaxy towards the top is kind of comparable. But then on the right, we have a picture in the infrared from the Spitzer Space Telescope, where now the blue images on the image have been tied to 3.4 micron light, and the red have been tied to 8 micron light. And you see the picture looks really different now, because you can see now that the galaxy to the bottom is filled with material that is emitting at 8 microns. That happens to be dust in the interstellar medium. And the stuff at the top has very little 8 micron light. It's being dominated by 3.4 micron light. That's because it's being dominated by the light from old stars. So the details here are not super important. I'm just trying to give you the sense that we really need to study galaxies in different wavelengths, and that because we're learning different physical processes, but also to remind you that when I show you images here coming up, that these images are false color images. They're combinations of filters that the instrument in James Webb is working at, and you are, so it's not like what you would see if you look at it with your eye, sensitive to particular, blue, green, and red images, as we see it. We have tied the colors of different filters to those images that we can process. Okay, so I've now told you about stars, so now let's talk about galaxies some. So what is a galaxy? So a galaxy is a collection of stars, but that collection of stars is there because the gas has collected in the center of a larger halo of dark matter, and the gas sort of pools into this large bath of dark matter and gas, and then the gas cools towards the center, forms the stars, and eventually it sets up these rotational structures. So that's the story of sort of how things go towards small scales. Material just, gravity pulls things along, tries to bring things down to small scales where the stars will form. But those stars are so energetic, the nuclear fusion energy in those stars is so powerful that the stars also tend to blow stuff back out. They're pushing the gas back out. So the gas can't just run away cool to the center and form lots of stars. It's being blocked by the fact that last year's stars are blocking the formation of next year's stars. So this is a self-regulated process. And that means that studying galaxy formation is really about understanding how these two aspects stay in balance. And a lot of the reason that we, when you have two things that are balancing, it doesn't take very much to tip things one way or another. So you end up being, mild changes can really affect the outcome. And so we hope that by studying galaxies, we can really tease apart what these effects, which of these effects are mattering most. Okay, so what I'll show you next is if I can, let's see if I can. There we are. So this is now a simulation of the formation of a galaxy, actually run by a group that includes one of the members here at the IOA, Deborah Shizaki. But you'll see, if I can get this to work. There. So this is the gas coming in on scales. This whole picture across is something on the order of 500,000 light years, so pretty big. But the gas is coming together in the center there over here, you're seeing the dark matter. Over here, you're seeing the stars getting formed. And I'll just let this roll for a bit. But you can see the gas coming in, forming these rotationally supported regions, and starting to form stars in this simulation. So you can see it's not a spherical, it's not, this is a complicated, influx of material, but it has successfully formed a rotationally supported disk, which I think they're going to spin around here to show you that they can do something that makes it look like a galaxy. And I think over on the left there now, I'm going to stop the movie here, but they're going to showing things about temperature and metallicity and so forth. So as time goes on, something might come in and smash into it and kind of disturb it, and so eventually manages to restore itself. So these simulations have been, a really big improvement in astrophysics over the past 10 to 15 years. If we were in this room 15 years ago, the movie would not look anywhere near this good. They basically couldn't form things that look like galaxies, but now they do a pretty good job. Okay. All right. Now the problem is that's a theory. It's a model. How do we actually figure out if it's true? And we want to do this, of course, by studying the properties of galaxies across cosmic time. Okay, so we want to look a long time ago in a galaxy far, far, far away, as every astronomer knows, because basically, when you want to look into the past, want to study things in the past, a way to do this is to look at objects that are so far away that the light has taken that long to get to you. Basically, by looking far away, we're using the fact that the finite speed of light means that you're looking back over gigantic periods of cosmic history. So we have the challenge in studying galaxy evolution that galaxies are evolving over the span of millions and really billions of years. And we don't live that long. And so galaxies really don't change on the time scale of any one person or any one civilization. And so we really only get to see any one galaxy as a snapshot. And our job of figuring out evolution or trends in galaxies is to look at large populations of these galaxies and to compare them across different epochs. This can be really challenging and almost ill-posed. It's like if I came in and showed you a picture of a baby nursery, a kindergarten, a high school graduation, a 50th reunion, and then said, okay, well, which people turned into which? Not so easy, right? So you're basically trying to figure out how can you piece together trends in one population and actually track them through. Okay, so because it's important that we study things early on, we really have to study galaxies that are very far away from us so that the light has taken billions of years to get to us. And this immediately drives you to need large telescopes because you're, by construction, looking at things that are billions of light years away, which is a very far distance. So these things are, although they are intrinsically relatively luminous, they appear to us to be extremely faint and small. And so that's why astronomers are always pushing to build larger and larger telescopes. But if you just go and image a piece of the sky, how do you actually figure out which galaxies are actually far away? Because you don't know intrinsically whether the galaxy you're looking at is a big galaxy, or like an intrinsically big galaxy far away, or an intrinsically small galaxy right in front of your nose, because galaxies, in fact, vary by factors of thousands in their mass and size. So the way that we do this is with something called cosmological redshift. And the idea here is that because the universe is expanding, the light that travels to us is being stretched. And so in particular, well, maybe I should say it differently. So let me try to give this version. So, if you all sat down in your chairs here in the middle, here in the front, and then I said, okay, in a moment here, everybody stand up and move so there's one extra seat between you and your neighbor, then you two would move by one seat. But you two would have to move by 3 seats in order to do it. And since this all has to happen in the same amount of time, that would mean that you two are moving apart by a small velocity, and you two are moving apart by a big velocity. So the fact that the universe is expanding is naturally giving rise to the idea that more distant objects are traveling away from us further. This is called the Hubble law, that basically by measuring velocity, we are getting a proxy for distance, because the more distant objects are moving away from us faster. So the amount of this velocity, because there's a velocity involved, the light that comes to us is suffering from something that's effectively like a Doppler shift. And so, as you sort of know, if you think about a car moving away from you, the pitch of the car is a little bit lower. We have the same issue here, that the light that was emitted by a galaxy at a particular wavelength is actually received here on Earth at a wavelength that has been stretched because of that velocity. So you can actually see this in these images of spectra on the right here. So these are spectra, so wavelength across the bottom in a funny unit, don't worry about it. And the plot is the plot of the frequency. But if you see where I've marked the red arrows, there's this characteristic little double notch. That's a particular pair of absorption lines from the element calcium. But you see that in these different galaxies, you can see that pair of lines marching across in the spectra. So the calcium is being shifted to redder and redder wavelengths, which corresponds to more and more Doppler shift. And so the galaxies at the bottom, the light has, those galaxies are moving away from us quickly, and therefore those objects are far away. And so the ones at the top are about 600 million light years away. The ones at the bottom are about 5 billion light years away. Now this effect is really quite strong. The light here that was emitted natively at about 4,000 wavelength units here has been shifted out to 6,000. That's a 50% change in the wavelength of light. That's crazy. It means that these things are moving away from us effectively at half the speed of light. So we call this redshift, and I'll be saying the word redshift a lot in the rest of the talk. And the thing I want you to remember is that larger redshifts correspond to larger velocities, larger distances, and because the distances are larger, that's a longer time that the light's traveled, which means that those galaxies are younger. They're coming from earlier in the universe. So higher redshift is mapping to earlier in the universe. Okay, so we want to study the early galaxies, and we now believe that the first generations of galaxies started forming just a few 100 million years after the Big Bang, when the universe is something of order 5 to 10 to 20% of its current size. So the universe has expanded a lot since then. And this means that these galaxies are very far away, about 13 billion years of light travel time. But it also means that the wavelength of light has been stretched by a huge amount, typically by factors of order 10. So light that was emitted at 4,000 of those units gets received to us at 40,000 of those units. Light that was, so 0.4 microns gets shifted to 4 microns. And that means that the light from stars like the sun, or even hotter versions of the sun, whose light was emitted in the optical and ultraviolet, those wavelengths have all been stretched by a really large factor, and it's moved all that light into the infrared. So, normal telescopes that you use in your backyard, or like the Hubble, these are built around optical light. That's great when you want to study nearby galaxies, but when you want to study galaxies in the early universe, those telescopes don't help you anymore because the light has all shifted out into the infrared. So I've already motivated that these things are really small. We need a large telescope. Now we need a large infrared telescope. Okay, so that is why the James Webb Space Telescope is a large infrared telescope, is that we need to be able to look at these galaxies, these faint galaxies early on. So here is a life-size model of the James Webb Space Telescope with a small fraction of the people who spent 2 decades of their lives building it. So it's a marvelous thing. So JWST at $10 billion is the largest astronomy mission since the Hubble Space Telescope launched 30 years ago. And it's been a really long time coming. JWST was the top priority of a decadal survey in the US in the year 2000. So basically got started in the mid-1990s, and that, people were pushing for it, and they got adopted in 2000 at a cost that was something like $800 million. And then there were massive cost overruns and schedule growth and lots of challenges. It was nearly canceled by Congress in 2012. So it had a very torturous history. But now it's actually been successfully launched and deployed. And although it is, certainly later than we hoped it would be when we started, it is so unique that it will still be just an amazing, unbeatable facility. Okay, so JWST is optimized for light between 1 and 5 microns, although it can work out to 28 microns. And so let's just talk about why. So the first is the idea that I've already explained, that for galaxies and early galaxies, the key diagnostic features have all been shifted out into the infrared, and so we need to work out there. But there's other major drivers for working in the infrared. One is dust. So interstellar space is filled with little particles, little smoke particles that tend to absorb light, and they absorb light preferentially in the blue. And so redder light, infrared light in particular, is able to see through the dust. We also have objects that are cold that we want to study, such as planets or certain kinds of cool stars. And so that emission peaks in the infrared, not the optical. There's also important diagnostics that certain molecules tend to emit in the infrared. So there's really wonderful things to do in the infrared. So infrared astronomy is a large field of study, has been for many years, but JWST is just their dream scenario. Okay, so why do we need to, why is infrared astronomy so important to do from space? Because we could be saying, well, we need infrared astronomy, let's just do it on the ground. And the reason that infrared astronomy is really hard on the ground is that, remember that, when you look in the infrared, if you go to a museum and they have the little camera up so that you can, see the people walking by relative to the background, right? Everything is glowing in the infrared. And in particular, once you get out beyond 2 microns, everything at room temperature is glowing. And in particular, your telescope is glowing. So it really is a huge problem. And so because of the glow of the telescope and the atmosphere, if you're working at sort of 1 to 2 microns, space is 1,000 times darker than the ground. And that's a gigantic opportunity. But as you go up beyond 2 microns, it's more like 1,000,000 times fainter than the ground. So there's just, it's enormously darker. And the reason, and so that's the big reason, like we got to go to space because we got to get the telescope and the atmosphere away from all this warm stuff. Now, if you're in space and you're using a properly cold telescope, then the foreground is actually coming from sunlight, and it's coming from sunlight that has come out from the sun. You're not looking towards the sun, of course, you're smarter than that, right? So you're looking away from the sun, but there's light that comes from the sun, hits little dust particles out in the solar system. Usually like meteorites have banged into each other and they've caused a little bit of, spray of particles. So you're getting backscattered light from all that dust, and that's the primary problem. But also, some of that dust is actually absorbing the light and glowing itself in the infrared, although it's somewhat colder temperatures. So the light that's being backscattered is preferentially blue for the same reason that the sky is blue. Things scatter more easily in the blue. So that is peaking the optical like the sun and is then getting less of a problem in the infrared. It's over here. And then meanwhile, the dust is thermally emitting, and that's coming up farther in the red. So it turns out there is a dark window at like 2 to 5 microns where the emission from the solar system actually reaches a minimum. And so this is the great opportunity, that there is this dark window out in space, and all of these really useful astronomical signatures have shifted exactly into that window because of redshift. So we want to build a cold telescope that can take advantage of this opportunity. Okay, we also need a large telescope. I think I'm going to skip this, but we need a large telescope, not just to collect the light, but also to make sharp images. I'm going to move past that. Okay, so JWST is a technological marvel. I mean, it's just amazing. Some people have credibly said this is like the most complicated thing humans can build. Like it's like kind of really at the limit of what humans can reasonably put together. It's a huge shield the size of a tennis court. The telescope hides behind this sunshade so that it can cool to outer space. But you can't just do that around the Earth because then you would be seeing the moon. And so you actually have to ship this thing out beyond the orbit of the moon so that it can sit out there and put the moon, the sun, and the Earth all behind the sunshade and hide in the cold. It's too big to fit in the rocket. So they actually had to fold it up like a big origami problem to actually fit it into the rocket so they could actually launch it, which means that when you get out into space, it all has to deploy. So this thing that's the size of a tennis court all has to carefully deploy out, and it's incredibly thin and fragile. It has to be really light because rockets are expensive. And so it actually weighs only 60% of the weight of the Hubble Space Telescope, even though it's considerably bigger. And that has things like the mirrors are made of beryllium because beryllium's really light. Oh, by the way, beryllium is also really toxic. So that means that all the protocols for polishing the mirrors had to be safe. And then you have this major problem when you're trying to build something cold, that when you cool things down, things are going to shrink, right? Colder, there's a coefficient of thermal expansion. As you cool things down, they shrink by noticeable amounts. And so, first of all, you're trying to build this amazingly precise optical system, and all the things are going to shrink, which means all the distances are going to move, everything is going to warp, and you have to predict all that. So they actually, when they're polishing, they would polish the mirrors and then cool them down, see what the errors were, bring it back up, predict how they need to polish, and then repeat as needed. They got very good at it, so they didn't have to repeat too often. Okay, so yes, you have to build things so they are cooling and getting to the, shrinking and getting to the right shape. But the problem with shrinking things is that some things shrink more than others, and that puts stress on stuff, right? So you can't, if you are holding a lens and the thing that's holding it is shrinking more than the lens, then it's going to crunch the lens. We did that. You don't want to do that. Okay, so that's like, you have to design around all that. But then the other big problem with cryogenics in space is that you're going to launch it. And when you launch it, it's subject to enormous shaking forces. So, when you have something that's going to shrink and be delicate, you would like to sort of not be holding it very tightly because you want to not, when you go to shrink it, you want it to be gently handled. But if it's going to have to survive shaking, you have to be able to hold it tightly, right? So there's this dance of like, how do you build things that can survive the shaking and then not usually by being strong, but then not crush things when this very strong thing changes its size. So that's a very difficult problem. And oh, by the way, the final tolerances are about 100 nanometers. So that's the wavefront error that eventually gets done. So lots and lots of challenges. And then the other challenge is, this thing is going to cost a lot of money and therefore cannot fail. And once you say something cannot fail, you have to spend more money to make sure that it doesn't fail. But now it costs even more money, so it really can't fail. So you have to spend more. So you get in this sort of vicious cycle of like your risk aversion causes the cost to run away, which makes you more risk adverse, which makes so terrible. Okay, so I won't go through some aspects of Webb. I think they're better. I'm sure they're better illustrated on various TV programs at this point. But the whole thing has to unfold. There was the stories of the 28 days of panic or whatever. But so getting this stuff all to work was really something. Okay, so NASA and ESA gave astronomers the best Christmas present ever. In Christmas 2021, when the telescope was successfully launched. It was actually launched so well that the mission lifetime got extended from 10 years to 20 years because they managed the orbit insertion to be so perfect that they don't have to use so much fuel to maintain the station. So that's great. So, after 20 years, really more than 20 years, of just design, development, review, construct, test, retest, worry, like all possible things, it all actually worked. So it's great. So zooming in, The stuff on the left is the previous best at 8 microns from the Spitzer Space Telescope, which, by the way, was fantastic and like did tons of stuff. But that's the picture on the right from James Webb, and you know the difference is enormous. And the sharpness comes from the fact that it's a big telescope. This telescope on the left was 85 centimeters. This telescope on the right is 6.5 meters, and you just see that performance gain over and over and over again. Most things in these wavelengths you're gaining as the fourth power of the diameter of the telescope. So this thing in reasonable units is like 6,000 times better than that thing. Of course, beautiful pictures everywhere you go. This is the image from the first light released image. Here's another pretty galaxy cluster. Nearby galaxies are really cool in James Webb when you start pulling together these different wavelengths of light, and you can see the combination of the gas and the stars all coming together. Here's another marvelous example of this. Galaxies can be kind of a train wreck. So, I mean, the depth of these images, honestly, is really almost disorienting. I've spent a lot of my time over the past 10 years working on ground-based images, and you know, a good image from a ground-based telescope, not the best, but you know, a good solid effort on a ground-based telescope is on the left. And there's the James Webb image of that yellow square on the right. You know, it's hard to even see which objects match up to each other. That's what I'm saying. Like, you go to look at the image, I can't even figure out. I have to really figure out, like, which is that? Like, the brightest star in this image is the very faintest thing over here. Like, so, you know, you can see that that galaxy there is that red dot there, and these galaxies at redshift 2.5 are not visible in that one. Even the galaxies at redshift 1.2 are not visible in that one. So it's just enormously different. And that's because galaxies are just, when you go to high redshift, the galaxy light has just been shifted out into the infrared relentlessly. That picture over there is taken in optical wavelengths. This picture is infrared. So here's a dramatic example. This is the image in the optical from Hubble Space Telescope. You see the big galaxy over there. But with James Webb, it looks like that. And there's an enormous, you know, an entire grand design redshift 2 galaxy, spiral galaxy, sitting there that just was not clear at all in the Hubble image. Okay, it is a really big improvement. So on the left is the deepest image at 1.6 microns ever taken with the Hubble Space Telescope. It took about 6 days of integration time. And the picture on the right is a picture with James Webb of the same area of the sky in about 9 hours. And we've already imaged many dozens of times more area than the Hubble ever covered at this depth. So the improvements are extremely clear. I focused on the imaging, which of course is very, you know, appealing. JWST also has just a marvelous spectroscopic instrument, and I think in many ways this is the more transformative piece of this, because we have not had ever access to deep spectroscopy beyond 2.5 microns, and this is just the critical thing for all sorts of studies. There have been many questions in galaxies, in the study of galaxies, where for 20 years the answer has been we'll have to wait for JWST, and it's been because we need this access to these spectra. And so it works great. A lot of these effort is actually with people here, so you should definitely have some of them come and give you talks. Okay, so I'm going to now be focusing on the work that I am involved with, again with colleagues here. It's called Jades, the JWST Advanced Deep Extragalactic Survey. And this is a project to do imaging and spectroscopy in two of the, I think, most iconic places on the sky, the Hubble Deep Field and the Hubble Ultra Deep Field. So coming back to the fields that were established with the Hubble Space Telescope for just looking out at the distant universe in a innocuous blank part of the sky to study galaxy populations at high redshift. These are important fields because ever since they got established, the community has just been going and observing these fields with the best telescopes they have. Every time you build a new instrument, you're going to go and do your best work in these fields because because the last people did their best work in these fields. There's a cumulative aspect of characterizing the galaxies here. And so it's been extremely important to us to go and do this field with James Webb Space Telescope. And so the instrument teams contributed about a month of mission time. We were given, about 2.5 months of mission time to do what we want, and we've spent about a month of it to go and do the deep fields here. So, zooming in on these images, they're just really remarkable. The detail that you get as you pan around, I'll give you more about that later. But so, these are just examples that I find particularly picturesque in the images. But it's important to remember these are really small images. We're talking about a few seconds of arc here in each of these. You just couldn't see things like this before. Okay, so as we try to go to the early universe now, so I need to say that, how are we going to identify these early galaxies? Well, we're going to do it by multicolor images. We're going to take images in multiple band passes. Why are we doing this? Okay, so there's this key aspect of things in the early universe that ultraviolet light. So this is a spectrum here from 1 micron on the left to 5 microns on the right. And what I'm trying to draw your attention to is this sharp break over here at 1.3 microns. So this is caused because the universe is filled with hydrogen, and hydrogen is the most common element. And hydrogen has the property that neutral hydrogen has the property that if it encounters a photon of 121 nanometers, then that will excite the hydrogen atom from the ground state to the first excited state. And then shortly after that, about a nanosecond later, it will de-excite, but it will emit that photon back in a different direction. So hydrogen is extremely good at scattering photons of 121 nanometers. And that means that ultraviolet light that is shorter than 121 nanometers gets blocked by the intergalactic medium. Basically, somewhere, if the light was emitted, at 110 nanometers, it would travel on, but then at some point, as it redshifts along and the wavelength stretches, it would come to 121 nanometers and promptly meet a neutral hydrogen atom, get scattered out into a different direction. You would not see the object in your telescope. So, basically, the ultraviolet is being completely cut off by the intergalactic medium, shortward of rest frame 121 nanometers. But this object is shifted out to a point where the light has been shifted by a factor of 10. So 121 nanometers has been shifted to 1.2 microns. So the signature we're looking for to detect these galaxies is, a nice picture of a galaxy here and then a complete dropout. So the reason I say infrared isn't just the best way, it's the only way, is these galaxies are actually invisible in the optical. There is no light coming to us from the optical. Only light that gets to us is in the infrared. So the way that we try to find these high redshift galaxies is to look in progressively redder bands. So this is 0.9 microns, 1.2 microns, 1.5, 2, 2.8, 3, 4, so forth, microns. And each row is a picture of a single spot on the sky in these galaxies. And you can see that in the top row, you have a whole bunch of nice dots. The galaxy is well detected, except in the 0.9 micron band where it's gone. So that corresponds to a case where that break in the spectrum was between 0.9 and 1.2 microns. That's redshift 9. The next line, okay, nice dots, but now it's gone both in 0.9 and 1.2 microns. So that corresponds to redshift 12. The next line, oh wait, now it's gone in 3 bands. 1.5 microns is gone. So these are called dropout galaxies because you basically come along and then the thing drops off. Is that making sense? Here's just the same idea going through again, where we have, at the top, microns versus flux, and you can see everything goes over and then a shelf at redshift 8. This one's at redshift 12. And here's one at 13. So in the early days of Jades, we're working really hard to process our images and try to find these examples, which are relatively rare on the sky. So you want to go out and be looking at the colors of these galaxies to find them. And the question then is, are these things actually at high redshift, or are we being fooled in some way? And the way to test this is to go and actually take a spectrum of the object so that you're seeing things that look more like the green lines on top instead of just the images. So we did that, and we were very happy to announce last December that indeed we had confirmed that these things were actually at high redshift, that these spectra do show sharp breaks indicative of the intergalactic medium absorption from redshifts 10 and 11, and we had found 12 and 13. So, this did really work. This is continuum spectroscopy, meaning, spectroscopy of the galaxies at levels way beyond what people have been able to do before. So just completely mind-blowing for those of us who work in extragalactic spectroscopy. Okay, so this is then the plot of redshift versus flux. And this is the candidates that existed in these fields before James Webb Space Telescope. So a handful at redshift 8, one provocative example at redshift of 11, which I'll come back to later on. So this was what we started with. This is as we published those first 4 objects, and a couple others got published. But earlier this week, we released our full catalog from these fields, and so now it looks like this. So these are 700 candidates at redshift greater than 8. We can't say that every single one of these is indeed at high redshift. There are sure to be some false positives in there, but I mean, just a huge leap forward in the field because of the ability to take these very deep multicolor images. And as I say, 93% of these are all completely new. So it's a huge step forward. We have been able to confirm from 42 of these that they were actually at high redshift. So we have acquired 42 redshifts of these targets, and we're 42 for 42 so far. So I mean, we're doing pretty well. But I do worry that we've taken the easy ones, so like we won't always do so well, but it's going pretty well so far. I think I'll actually skip that. Okay, so the next step is, what are these galaxies actually doing? Like, what are they looking like? And a lot of them are pretty complicated. So these galaxies with James Webb's level of angular resolution are no longer boring little blobs, boring single blobs. They actually have structure, they have features, they have color gradients, they have multiple components. So we're going to be able to now really dig into the properties of these galaxies. All right, so next up, I'll come back to this bright example from redshift of 11. So, we were really super excited to find these first 4 spectroscopic confirmations of these high redshift galaxies. But we were a little disappointed, maybe a little bit strong, but we were a little let down that we saw the sharp continuum break, but we didn't see any lines in the spectrum. And so that's not as gold-plated a proof as you'd like. And it was understood why we were not seeing these. The strongest lines had all shifted out even beyond James Webb's capture range for the infrared wavelengths. But this changed with this brighter object, GNZ11, which is a considerably brighter object, about 10 times brighter than the candidates I was showing you before, which was known previously from HST, and we were able to observe it with our imaging and spectroscopy in early February. So here it is in imaging. This is a paper led by Sandra Takela, who's over here. He works here at Cambridge, and you can see again just a quintessential dropout galaxy. Super duper detections, and then nothing at 1.2 microns. Certainly the imaging encouraging us that this is indeed at high redshift. But I think the real wow moment was when we got to go and take the spectrum, and sure, you see this amazing ultraviolet break, but all these emission lines dancing across the spectrum were, just a wonderful thing. These emission lines are how we get to study in detail about the chemical enrichment of the galaxies, the dynamics of the galaxies, the star formation rates of the galaxies. So there's lots of diagnostic features in these emission lines. And so this really, I think, sets us on a path to studying these kinds of galaxies in more detail. Also very encouraging is that GNZ11 does not appear to be alone. When we look at the field, we see other galaxies that appear to have redshifts consistent with that object. So it's not just that you're studying that one object, you're studying it in the context of its environment and how it might be forming. And we see other examples in our data of these sort of overdense clumps of galaxies. So as I run towards the finish here, I mean, JWST is really revealing large populations of galaxies at high redshift. And for me, the primary takeaway so far is that these populations are really heterogeneous. If you had a simple story, we like to tell simple stories in astronomy, and so you have this simple story of galaxies are going to look like this, they're going to do this, and then you sort of start thinking that all galaxies are going to be the same because they're all going to look like that particular fairy tale. And in fact, they're really complicated. We see these complicated morphologies, groups. We see the spectra aren't all the same. There are variations in line ratios and star formation rates, and the group here is doing lots of work on just trying to understand how complicated these things are. We're starting to see variations that are in revealing properties of the intergalactic medium. So it's really important that we be able to look at these objects in larger sets so that we can sort of see these variations, and also that we can look at each individual galaxy with enough precision, enough sensitivity that we can actually see how it is different than its neighbors or than its partners. And Jades and JWST are going to allow us to do this really, really well. So we're just pushing deep to try to reveal the frontier at redshift greater than 13. And I think we're just in very early days. You've been seeing probably stories in the newspapers about various aspects. And I just have to say, these are just the first teasers of things. And some of them are more speculative than others. But we're just at the start of, I think, a multi-decade journey on this. So I want to encourage you to view the universe yourself. So there's a viewer. You might want to take a picture of this slide to, I'll show it again, but to get these URLs. So let me actually jump out of this and show you. Oops, not that though. Oh, sorry, it's over there. There, okay. So this is a viewer that you can use yourself. This is a public site. And if I can get over here. So this thing is really cool. You can zoom around. You can pan around on the sky, looking at all the galaxies. If you come over here, you can change what filter you're looking at and vary between the bands. If you come down here, I should zoom in before I zoom in here, you can actually see where we found all the objects. You can click on individual objects to see what the whole pattern is across all the bands. And if I come over to this one, is it going to do it for me? Yeah, okay. So if you oops, sorry, that's the wrong one. So you can click there and actually see the near spectrum that was taken. This one's at redshift 6.3. So it's this, we honestly in the team, we built this viewer so that we could actually explore the data because it's just overwhelming to deal with the complexity of the data otherwise. And I honestly, when I have a bad day and I've been in too many committee meetings, I just go and I browse the sky and I feel way better. So, but we've now been able to make it public because we've released our data on Monday. And so this is really the tool that we use. And so now you can use it yourself. Okay. Is it going to come back for me? Okay. All right, so I want to close by thanking the Jades team. Oh, I'll show it again. I promise. So I want to close by thanking the Jades team. It's been a great group of people to work with, and just end with the idea is that JWST has been a long wait, but it's here at last. It's going to be a transformative mission in astronomy. I focus on galaxies here, but almost all areas of astronomy are just deeply, deeply affected by what's going to be happening with JWST. It's critical for studying early galaxies, to cut through interstellar dust, to see the coolest stars and exoplanets. We are gratefully thankful and honestly kind of amazed that the launch and deployment and commissioning went as smoothly as it did. And the first months of science operations, that's been more than 4 months, sorry, but first year of science operations has been, I think, really a great success. So again, there's the slide for that, and I'll thank you and take any questions.
Thank you so much. It sort of seems like science fiction when watching.
To us too, yeah.
It's mind-blowing. Does anyone have any questions?
Please.
Can I just say thank you for what you do?
Oh, well, thank you. You all pay for it, so it's
I
Please.
was just going to say the observations that you picked up that were not previously visible to us or basically unknown, have we been able to tie any of those into modelling to sort of start predicting the outer reaches of the universe?
Yeah, that's the kind of stuff that's just actively going on right now as people try to build up the demographics of these populations. So I don't have simple take-home lessons from it yet, but this is absolutely what's going on, just to try to understand that. Please.
So, starting from looking at the different filters where you sort of drop out of the dots of the galaxies, did you take multiple measurements? With filters like over the whole?
Yeah, that's a great question.
Or?
Yeah, we do, but also let me just say, the way these instruments are built, you have obviously a telescope and it's focusing the light to an image detector, and that detector is sensitive to a lot of different wavelengths. So what you do is you slide a piece of colored glass in somewhere into the light beam that's going to reject light of most wavelengths and only pass through the light of the wavelengths that you want. So that's why it's called a filter, is that it literally is a filter that's been put into the field. So there's a wheel inside of the instrument that can rotate, again, at cryogenic temperatures, but it can rotate and change what you're looking at. So when we make these images, we're actually, we have to stare at that spot in the sky, take our image, then change the filter, stare at the spot of the sky, take the image, change the filter. So NearCam is fortunate it can do 2 filters at once because of a particular mechanism, but it's, you're just sequentially progressing through. So it's different from your digital camera or your phone, where they were very, very clever, and they have every little pixel in your thing actually has 3 little dots which are sensitive to red, green, and blue, and so you're getting the color image all in one go. That's not how any astronomical instrument works. Yeah.
Can I ask, we are exposed to the YouTube sensations and Parkour and Gus said, the Big Bang Theory is wrong, much more dense than what it's supposed to be. All that. Can you perhaps talk what you've now seen towards that? Give some context from your perspective.
Okay, well, the Big Bang being wrong can come in many different forms. So, I think that the evidence that the universe starts from a hot, dense state and is expanding out rapidly and cooling, I think is pretty incontrovertible at this point. We have evidence from lots of different paths. This is just one. But our model of the universe is more complicated than just saying the hot Big Bang. We actually have very specific ideas about how dark matter works, how dark energy works, how early universe might work to produce the structure in the universe. So when we really are talking today about what our cosmological model is, it's a much more specific thing than just saying that the universe starts hot and dense and expands. There's particular modeling on top of that. And so one of the things we try to do all the time is to figure out if that model is in fact correct or adequate, or if we're finding ways in which it disagrees. So, I believe at this point that we have not found any deviations in the model, in that underlying model. It's still early days. There have been people claiming that these high redshift galaxies are too extreme and that they would, quote unquote, break lambda CDM. I am not on that camp. I just think it turns out, I think the modeling is more complicated, and so I don't think we're there yet. But So mostly I view these data as a route to studying how galaxies are forming in the cosmological context, as opposed to being a way to study the cosmological context itself. However, there are people who think that we can use these data in some ways to actually push on the cosmological context. So eventually I think we will get into some of those ideas, but we're just not there yet. In the back.
I'm interested about the spectra you showed for Jades at 11, that one particular object. And you mentioned the absorption lines, the bumps that you highlighted with dashed lines.
Right.
They could each tell you something about the property or the behavior of that particular galaxy. Can you pick a few and tell us what they mean?
Oh, okay. Where'd I go here? There we are. So it is, so the ones over here, the two on the right are, well, I guess so, okay. So these two are emission from hydrogen, and that hydrogen is primarily excited by hot young stars. So these are a classic way to try to study the star formation rates of galaxies. And all the rest of them are being produced by some atomic element, oxygen, magnesium, carbon, nitrogen, in different, with different ionization states. So some of these are doubly ionized, some of them are singly ionized, some of them are triply ionized. Atoms get ionized in space because when they get hit by an ultraviolet photon and pop an electron off, that electron wanders off and might not come back, or that atom might sit in that state for tens of thousands of years, because space is so empty that once you knock things apart, they can't find each other again. And so the details of how much stuff is in highly ionized states versus less ionized states is telling you about the temperature of the gas, and also, sometimes the density of the gas, and also about the hardness of the ionizing source that is shining on them. So a lot of these things are taken in ratios to try to understand either the composition of the gas or the nature of the ionizing source that's illuminating them. Please.
This is a question for my son, actually. What is the oldest galaxy that you've seen?
That one. I mean, that's the oldest one that's been confirmed so far. Now, when we go on to this slide, that one is probably that thing there. So we do see things that are at higher redshift, perhaps, but the question is now, can we prove it adequately? So the current record holder is that one. 350 million years after the Big Bang. Please.
Picking up actually from this slide, you were saying that potentially you've actually already found the easy to find ones. How do you actually work out which areas to analyse?
Well, what I was trying to get across there, perhaps too obliquely, is that, look, the redshifts, when you can get a successful spectroscopic redshift, it's usually because it has a very strong emission line. And we, I think, are better, it turns out I think we are better at putting the objects on this plot if they have strong emission lines. And so I'm a little nervous that we may, the hardest things on this plot will not have the strong emission lines, and so they'll be a little harder. But, the truth is, with the exception of the 4 galaxies that I showed you, basically everything on this plot has been observed kind of serendipitously. It wasn't that we yet had been able to plan an observation to do it, because it turned out that almost all of our spectroscopy got delayed in time. So this is a good thing. We have like this big pool of candidates that are ready to go, and we're going to get spectroscopic time in October, and we'll be able to mow into these things and see how we do. Yeah. But some of them are really faint. 30th magnitude is crazy faint. That's 10 billion times fainter than the faintest star you can see in the sky with your naked eye. So.
Well, if there are no more questions, so first of all, can we thank our speaker again?
Thank you.
So secondly, 2 quick housekeeping points. The second thing is that, by coincidence, there is actually a second talk on tonight. The Cambridge Astronomical Association are running their Introduction to Astronomy course. They're very kindly let us have the room and do a talk later on. So they're going to come in after this and have a talk all about dark matter and dark energy. You guys are very welcome to stick around for it. If you like, after the break, completely up to you. So yeah, thank you so much for coming. There are some questions outside.
Thank you.
Thank you so much.
Yeah, this was great.
Wonderful. After those super